This is Lab 5 on the falling slinky. The purpose of this lab is to measure and predict the motion of the bottom of a vertically oriented slinky when it's dropped. The steps we will take for this lab are to use Tracker to collect data points from our video that we're observing, use GlowScript to create a computed model of the system, and to analyze our data. So, first of all, our physics principles will be incorporating Newton's first law, which is stating that an object at rest stays at rest and an object in motion stays in motion with a constant velocity unless acted upon by an unbalanced force. We'll also be using Newton's second law, also known as the momentum principle, stating that the net force acting on a system is equal to the change in the system's momentum over the change in time. And from that equation, we can derive the velocity update formula stating that the final velocity is equal to the initial velocity plus the net force acting on the system divided by its mass times the change in time. And from that, we can get the position update formula stating that the final position is equal to its initial position plus the final velocity times the change in time. The forces acting on the system are the force of gravity, which is equal to negative mg j hat, m being the mass of the system, g being the gravitational constant, and j hat being the unit vector in the positive y direction. There will also be drag force, which is negative b times the magnitude of velocity squared times v hat, b being the proportionality constant for the magnitude of the drag force, and v hat being the unit vector of the velocity. There will also be the force of the slinky, which we can also just call the force of tension on the system, which is equal to mg j hat, which is in the opposite direction of the force of gravity. And the net force is going to be all three of these forces summed together. So for our video, we observed this falling slinky and we chose the origin as the bottom of the slinky and observed the y position to the bottom of the slinky as it fell. The initial conditions we're going to input into our computed system are the mass is equal to 0.21 kilograms, the initial position is equal to 5.255 times 10 to the negative 3 meters, and the y direction being negative 5.255 times 10 to the negative 3 meters. The initial velocity is going to be 0 meters per second. So for our GlowScript code, you can see that we changed the values of the initial position, mass, velocity, change in time, gravitational constant, and the proportionality constant we got as 5. And so I adjusted the times of both the while loops to be the first as 4.333. That's the time right before the bottom of the slinky begins to fall. And 6.833 on the right, we can see here, is the time at which the slinky hit the floor. And so right here, we can see force of gravity and the force of tension. And since the force of gravity and force of tension are in opposite directions but equal in magnitude, the ball.vel and the ball.pos of the bottom of the slinky is going to be 0. So we should expect a horizontal line for this section of our code. And for this section of the code, we use the force of gravity and the drag force as the bottom of the slinky is falling with the entire slinky. And so from this, we get these two graphs right here. And on the left is our observed positions from Tracker, and on the right is our graph from our GlowScript code. And as you can see, these graphs are very similar, almost the exact same. The only difference is that on the slope downwards on our observed position versus times, you can see there are just a couple of bumps that don't make the line straight, but we can just assume that these are from measuring error from taking in the positions on Tracker.